everybody. We have started our discussions on sensors, and we have discussed the static performance characteristics, how a sensor is specified, and we have seen that different definitions like what is sensitivity, what is your resolution, what is non-linearity error, and these kind of things. Say repeatability, stability, these things has been already defined, and we have discussed already position sensors, proximity sensors, and velocity sensors, isn't it? We have what sensor is used for measurement of angular velocity. We have discussed previously. কি সেন্সর ইউজ করেছিলাম previous day? What class was there? That was on optical encoders. How many types of encoders are there? How many types of encoders are there? Optical encoders. So we have already studied these things. Mechatronics, position and proximity sensor, position and velocity sensors. We have discussed about these optical and we were discussing about this Hall effect sensor also, and we described how the charges are separated when, and we know that a magnetic field, when a magnetic field is there in a space, and if a charge moves in that space, then it experiences a force, and that force is given by Q V cross V. V is the velocity of the charge, V is the magnetic field, V is a vector, magnetic field is a vector, and V cross V in that direction of this cross product, that magnetic force will be applied. And at the same time, if in that space some electric field is there, then the charge will experience the electrical force. That vector sum of this electrical force and magnetic force is known as, on a charge, is known as Lorentz force, and that principle is used in Hall effect sensors. There what happens, a current flows. So suppose current is flowing in this direction, and so the charge carriers, if it is a metal conductor, then charge carriers will be electrons. So electrons are moving in this direction, there will have some drift velocity, and due to that they are moving in this direction, and magnetic field is there, and due to that they experience a force. So their direction of velocity is this, say. So this is the velocity direction, and the magnetic field is in the lower direction. So V cross V, by this right hand thumb rule, we can see the magnetic field is in the direction coming out of this pole. So in this direction magnetic field, but the negative charge is there. So the moving electrons will experience magnetic field in this, not this direction but this direction, because it is negative charge. So electrons will be accumulated here, continue to accumulate here, and in this direction of this plate there will be lack of electrons, so positive charges. So separation of positive and negative charges. So in this direction positive charge and here negative charges. That means what it is, an electric field is being produced, and the direction of electric field is not this positive charge and negative charge. So electrons, a positive charge will experience force in this direction, so electrons will experience a force in the opposite direction, that is this direction. So there are two forces. The magnetic force is acting in this direction going into the pole, and due to electric force the electrons are experiencing force like this. A time will come when that electric force and magnetic force will be equal, and at that time it will stop. That is, that movement of electrons in this direction will stop, and a stable configuration will come where this as a result a stable voltage potential difference will be there. This potential difference is known as Hall potential. Are you getting the point? Any confusion? So this potential is known as Hall potential. Now, as the magnetic, if the magnetic field is now increased, what will happen? The magnetic force will increase, so more separation will be there. As a result, electric field potential will also increase. That is the Hall voltage or Hall potential or Hall voltage will increase. So by this movement of this magnetic field, the Hall potential measured between this side of this plate and this side of this plate, what will happen is that the Hall potential or Hall voltage will change as this magnet is moved. So with an object we can place this magnet. As the magnet is coming closer to it, the Hall effect sensor can produce the Hall voltage accordingly. So two types of things can be built out of this. One is so these are the mathematics. We can see that the Hall potential or Hall voltage is equal to Kh into V into I by T, where Kh is a constant. We call it Hall coefficient. V is the strength of magnetic field. Magnetic field also known as magnetic flux density. I is the current flowing through the plate, and T is the plate thickness. So for constant I, V is proportional to B, the magnetic field or magnetic flux density. Two types of Hall effect sensor can be there. One is linear. Hall effect sensor is many times used as range sensor also, and it is widely used in industries too. Why this is used in industries? Because it is robust. It can endure severe conditions, say chemical plants, where Hall effect sensor can be used. And two types of, one is linear, that is according to displacement or according to the distance or range, the Hall potential will continue to change linearly. And one thing can be done as threshold. So if a particular distance, if the object comes to a particular proximity, particular closeness, then only it will trigger a switch. It can be done like this. So that is known as the threshold type of Hall effect sensor. Fine. Now, I have already described this. Some applications are fluid level detector. So imagine there is suppose a chemical power plant, processing plant is there, and there is a tank, and in that tank a particular level is to be maintained. Suppose the level is this. Now you can place a float on it, and at the top of the float you can place a magnet, and at a certain distance on the top of this container you can place your Hall effect sensor. Now as the level is increasing, so your float will be lifted upwards, so the magnet is coming closer to it, and you can preset a particular value of this distance where the Hall potential will reach a particular value, and a particular switch will be triggered, and that flowing will be stopped. That is, filling of the tank will be stopped, and whenever this level decreases, then again that filling will start. So a pump will be on, switched on. Fine. So that is in brushless DC motors. In brushless DC motors, when we will discuss about your electrical drives, we will see that how DC motors act. You probably a lot of you know how DC motors act. And in case of brushless DC motor, there will be no brushes. There will be rotor, there will be stators. Say rotor is inside and stators are out in a cage. And whenever the rotor is coming to particular position, the stator is to be switched on, so that it will give a force, magnetic force. As I described you, that Q FB, that is magnetic force, is equal to QB cross B. So accordingly, it will experience a force at a particular instant. Those stator windings at different locations, those have to be switched on. So on all of these, some Hall effect sensors can be attached, and whenever the stator is being aligned with this, that particular winding will be switched on, and it will continue to rotate. So this is the principle of brushless DC motors. So in that case also, that Hall effect sensor can be used. One is tacho generator for velocity measurement. Say what is happening here is that there is mistake here. These are toothed wheel, and it is made up of a ferromagnetic material. Okay, and there is a pickup coil or a winding is there. Okay, and it is a magnet, and due to this magnet, this surrounding or this coil is subjected to some magnetic flux. But that whenever nothing is happening, the magnetic flux is constant, nothing will happen. But as soon as this is rotating, this due to this tooth the permeability of this space will change periodically. Okay, in a periodic manner, as it is moving in a say constant speed, constant RPM or angular velocity, the magnetic flux around this space will be changing periodically. Why magnetic flux will change? Because permeability will change. Amount of ferromagnetic material present in a space determines the permeability of that space. Actually, what is permeability? Whatever magnetic field is there, suppose a magnetic field strength of something Tesla is there, say 1 Tesla is there. Okay, now if you place a ferromagnetic material which is having say permeability of 4000 to 5000, then the magnetic field in that space will become 4000 to 5000 Tesla. If it is of soft iron or pure iron, it will be 20,000 times. Okay, for general steels which is 100 ferromagnetic material can be this like this. So as it is rotating, magnetic flux subjected to is changing periodically. So according to Faraday's laws of induction, EMF will be produced, and that EMF is the magnitude of peak amplitude of that EMF will depend on this RPM. How? Let us see. So these are the explanations. So the magnetic flux can be described like this: phi is equal to phi naught plus phi cos n omega t. Phi naught is the mean value of the flux, and phi is the amplitude of the flux relation. And periodically it is going. So we have seen a sinusoidal function, cosine functions. And if E is equal to minus d phi dt, so we are doing this. N is the number of turns in the coil. So n phi, small n is the RPM of the wheel. So n omega sin n omega t. So this Emax sin n omega t. So this Emax, we can see that it is dependent on n phi n omega. So omega is the changing. N is the number of n is the number of teeth in the tooth wheel. So and capital N is the number of turns, and phi is the that is the amplitude of. So these are constant, isn't it? N phi n, this is constant. So Emax is proportional to this omega, that is angular velocity. So measurement of this E omega is proportional to angular velocity, so that peak amplitude can be calibrated. Peak value of this generated EMF or induced EMF can be calibrated against your angular velocity, and that will define your angular velocity. However, there we can use some signal conditioning devices which will produces number of pulses as the value of this Emax. So number of pulses will be a direct indicator of the angular velocity. AC generator, it is a simple principle of generator, and like same in a permanent magnetic field, a coil is rotating, and this coil can be attached to the shaft of which we want to measure the angular velocity. So as the shaft will rotate, so it will rotate, and as the coil is rotating in a magnetic field, so the magnetic flux subjected to this will be varying, and as a result, a sinusoidal EMF will be induced. And as previous, that the peak amplitude or the RMS value of the induced EMF will depend on the angular velocity. Okay, or directly proportional to the angular velocity. So this can be a measure of angular velocity like this. So AC generator can also be used as a sensor. So this is the construction. I guess all of you know this. Pyroelectric sensor. In case of pyroelectric sensors, what happens is that there are some materials, ferromagnetic materials. What is ferromagnetic materials? In case of ferromagnetic materials, what happens is that there are magnetic dipoles within that material. You know the theory behind it. There are magnetic dipoles within the material, and whenever external magnetic field is applied on it, what happens is that internal magnetic dipoles align with the external magnetic field, aligns themselves with the external magnetic field, so that particular matter becomes a magnet itself. Okay, so that is induced magnetism. That is the principle of induced magnetism. Now there are some materials upon removal of the external field. In most of the materials, what happens upon removal of the external field, these magnetic dipoles due to thermal agitation will again be lost. That is, the polarization will be lost, and it will again behave like normal. But there are some materials upon removal of that external magnetic field also, those alignment or this polarization of the magnetic dipoles remains within this material. So it becomes a magnet. So that is ferromagnetic materials. In the same manner, there are some dielectric materials which are ferroelectric. You know, in most of the materials, most of the dielectric materials, the molecules are dipole, polar molecules. That is, they have some electric dipole moment. Okay. So whenever some external electric field is being applied, these dipoles are trying to align. Suppose in this direction electric fields are there, so they are trying to align themselves within that with that electric field. As a result, there will be in one surface there will be positive charges, and in the opposite surface there will be negative charges. So separation of charges is there, polarization of electric charges will be there. As a result, electric field inside electric field will be produced also. However, as the external electric field is being increased and increased, a point will come where all the molecules, all the dipole or polar molecules are aligned. So that is known as saturation. Okay, so maximum that can be done. But upon removal of that external electric field again due to thermal agitation, this polarization is lost. But there are some materials which are known as ferroelectric materials. For them, these upon removal of that external electric field also, this polarization will not be lost. It will be kept. Now, as temperature, if now this substance is subjected to some temperature, then amount of polarization will decrease. So in general, it has been seen that with increase in temperature, that polarization decreases linearly. So that can be an indicator of the temperature measurement, and there will be a particular temperature at which all the polarization will be lost. That temperature is known as Curie temperature. In case of ferromagnetic materials also this happens. There will be a particular temperature. After if that is brought to the temperature, that then magnetism will be lost. That is Curie temperature. Okay, so the part, and there will be some signal conditioning devices because the charge generated is very low, and as this is being subjected to temperature, what will happen is that some charges will be leaked to the external circuit and it will produce some current, but that current is very low, say in the range of nanoampere, picoampere, nanoampere, or mostly microampere. So those cannot be utilized in our day-to-day devices, but we can use some damping there. Okay, and whenever this is the thermal energy and there are some amplifications and comparators, so some signal conditioning devices will be there, so that becomes a measurable thing, and whenever particular thermal object comes near to it, this will indicate as this current, and this will indicate some presence of some object. Okay, so motion detector for this can be used as motion detector also. Suppose this is placed in somewhere, and whenever a person pass by it, it is radiating some thermal energy, person born, so it will indicate that some person is born, or if some thing has been moved, or most of the materials emits energy, isn't it? Thermal radiation is always happening due to temperature. So if an object is passing by, suppose in a conveyor belt some objects are going on, so it can be used to count that. Is it okay? So applications of piezoelectric sensor include diffusion detector, as I told you, optothermal detector, pollution detector, position sensor, solar cell studies, and engine analysis. In these we have already discussed, these incremental encoders and how that can be used as resistor. Now let us move to another field. Force fluid flow sensors. This is the simplest way of measurement of force. All of you know from your school levels you are studying this, we have seen also. This is the spring balance. Now strain gauge load cell, we have already discussed strain gauge, how strain gauges can be used for measurement of displacement, isn't it, or say deflection of beams, etc. Okay, and the same things can be used as load cell. Okay, what might be the structure of that load cell? Suppose this is one load cell. Now two sensors will be attached in this manner and two sensors will be attached in this manner. So whenever some force is applied, these whatever applied the sensors which are attached longitudinally will decrease in length, and the sensors and the strain gauges which are attached circumferentially, okay, they will elongate. If you press it, these will shorten and these will be stretched. Okay, these two will be stretched, and you know the two elongating and two compressing strain gauges, if connected to particular arms in opposite arms properly, then it will give maximum sensitivity, and this force and this out of balance voltage in the Wheatstone bridge is proportional to this force, and that out of balance voltage in the Wheatstone bridge can be calibrated against this force, and it can be used as force measurement sensors. Okay, you have seen the applications of these kind of strain gauge in many shops, and all the shops you have seen nowadays. These kind of things are there. Actually, there is some load cells. Okay, pressure sensors. Similarly, the strain gauges can be utilized for pressure. The out of balance voltage can be calibrated against the pressure, and however, those are to be attached on a diaphragm. So it can be a diaphragm, it can be a corrugated diaphragm, it can be double corrugated diaphragm. So accordingly, as only diaphragm, then corrugated diaphragm, double corrugated diaphragm, and a below diaphragm. So these are the increasing sensitivity, increasing order. Sensitivity is in the increasing order of sensitivity that can be done. So that is the same principle will be utilized here. There are some available, commercially available pressure sensors are MPX 2100 series, pressure range of 100 kilopascal and a supply voltage of 16 volt DC with absolute pressure, and differential pressure forms a voltage output over the full range of 40 millivolt. The response time 10 to 90% for a step change from 0 to 100 kilopascal is about 1.0 millisecond, and the output impedance is of the order of 1.4 to 3.0 kilovolt. So these are some another you can see MX, MPX sensor, pressure sensors, MPX. Fluid pressure in the same manner. You can double corrugated means you can use capsules, you can use bellows, and these will have more sensitivity than this, obviously. Isn't it? And how this is done? So you can use this bellow or your capsule you can use, and on this you can put something. Suppose this is this will be the rod inside that. We have already studied LVDT, linear variable differential transformer. So that can be used. So now we have used this for displacement measurement. However, this output voltage can be calibrated against the pressure, then it can be used as pressure sensor. However, it can be used even capacitive sensor can be used here. The middle plate or the dielectric plate is being moving, or one of the plate is being moving, and it is attached to this bellow. So capacitive sensors. So in many sensors this can be used, or this can be utilized. And you know, Barden tube, helical spring tube, these can be used. Also these can be used as measurement of pressure and pressure sensor. Piezoelectric sensor. Do anybody know? Does anybody know what is piezoelectricity? Anybody? What is piezoelectricity? What is piezoelectricity? There are some materials, some crystals, which are known as piezoelectric material or which shows piezoelectricity. What is that? If that material is compressed or stretched, suppose it is compressed, then momentarily opposite charges will be generated on the opposite faces. And if it is stretched, then the reverse will happen. So suppose for compression, on the top surface positive charge and the bottom surface negative charge is being accumulated, and if it is stretched, then on the top surface negative charge and the bottom surface positive charges will be accumulated. So this phenomena is known as piezoelectricity. And there and with respect to that crystal, there will be a particular direction perpendicular to that direction. If you or according and in that direction, if you give the force, then there will be maximum generation of charges, and perpendicular to that direction, if you give the force, then no separation of charges will be there. Okay, and you should remember this. There is a particular direction. In that direction only this will happen. Now, as this, and one thing you must remember is that it is the charge generation is momentary. So at that instant, you have to know what is happening. So in general, these piezoelectric devices are used for measurement of dynamic quantities, say dynamic force, dynamic pressure. Dynamic, what do you mean by dynamic force? Dynamic means changing. Okay, not static. Static, in case of static force, it will remain constant. Suppose this strain gauge load cell, that can be utilized for your measurement of static force. But for measurement of dynamic force, that is changing force, and how and as the force is changed, so that amount of charge generation will be changing, and it is momentarily, and that can be tracked very well. So that for dynamic force measurement, pressure measurement, these piezoelectric sensors are widely used. Are you getting the point? And there are some naturally, quartz is one substance which is naturally occurring. We can say that Q is proportional to that H, that is amount of elongation or compression. Okay, that is amount of elongation or compression, that is amount of change in length. Okay, and this X is proportional to F, so we can say that Q is proportional to F, and this S is become a constant, and it is termed as charge sensitive. So naturally occurring crystal which shows this piezoelectricity is quartz. Quartz has a charge sensitivity of 2.2 picocoulomb per newton, and there are some synthetic materials like say barium titanate, which is having 130 picocoulomb per newton, and zirconate titanate having 265 picocoulomb per newton. Okay, so metals electrodes are deposited on opposite faces of the piezoelectric crystal. So these are the equations. Yes. Suppose this is the crystal, then metal electrodes will be deposited on that. So whenever these positive charges are being accumulated or in negative, so it will draw from the external circuit or environment negative charges, and it will move positive charges, so that charge neutrality. And whenever there is changing, suppose and it is changing, so amount of polarization will change or say decrease, and that on that electrodes whatever charge accumulation has been there, they will release it, and in the circuit we will see some current. Though this is very small in amount, however we have to use some signal conditioning devices like amplifiers, etc., so that can be done. Now, yeah, and this is your equivalent circuit. This is the circuit of this piezoelectric sensor, and this is the equivalent circuit. Okay. the cables will have some capacitance, the plate piezoelectric, the plate separation is there, that will have some capacitance. So we have to look into that, all those things. There will be some resistance also, and this is the equivalent circuit. Now tactile sensors. With this, this is a tactile means touch. This is touch sensor. This sensor can be say attached on the fingertip of robotic fingers, the robotic flippers, or on the fingertip of robotic flippers that can be used. And whenever it touches something or holds something, and with a particular pressure, then it will know that it has contacted something. Okay. How does it work? Here also piezoelectricity occurs. Here piezoelectricity and reverse piezoelectricity both occurs. In case of piezoelectricity, what happens is that if you compress or stretch, opposite charges will be produced. Now if it is sinusoidal, then what will happen? Sinusoidally opposite charges will be generated. So in the external circuit we will see sinusoidal current is being generated. Okay, in the piezoelectricity. And in the reverse piezoelectricity, what happens? When a particular say material which is having that property of reverse piezoelectricity, if this is if some alternating current is applied, then its surfaces will be subjected to periodic changes of opposite charges, and these opposite charges, it will elongate and compress periodically. That is the vibration will occur. Okay, so we use some piezoelectric field that is known as polyvinylidene chloride, PVDF. So there is a lower PVDF film, upper PVDF film, and in the middle there will be some say soft material for transmission. Now some AC input is given. Due to reverse piezoelectricity, this will vibrate. Okay, periodic compression and stretching means vibration. Through this soft film, this vibration will be transmitted to this upper film, and as this is vibrating, that is compression and stretching is occurring. This is also PVDF and piezoelectric film. So alternating current will be generated here. So that current is there. Now whenever you put some finger on it or some touch is there, then this alternating current which was being produced, that amount will be changed, and this change in output current will indicate that something has charged. Okay, you can use this as a monitor. Suppose in a monitor there is a monitor, and your say in horizontal rows are there of this PVD film, and some vertical rows are there in the PVD film. So as if these horizontal and vertical rows are giving you coordinates, there at a particular point you are touching, say 7 number of horizontal film and say 8 vertical film. So 7, 8, that coordinate position is being touched. Okay, so touch screen can be made like this, and in the robotic fingers also that can be used. Fluid flow from Bernoulli's equation, we are getting this, and fluid flow measurement can be done by you know this thing, so I am not describing it here. What is this? Continuity equation, Bernoulli's equation with this. Say orifice plate, I am not describing it here. Turbine flow meter. Turbine flow meter we have already discussed. Your tacho generator. Now suppose a particular turbine type of thing is there. Turbine is a small thing, and according to the flow it will rotate. And on its wings of that turbine, you are getting some ferromagnetic material. Then like that tacho generator, you place a pickup coil near it, and as it's rotating in the pickup coil, some magnetic field will be some alternating current will be induced or EMF will be induced, and with the same principle of tacho generator, you can measure that is fluid flow velocity or flow can be that external that number of pulses generated from this can be calibrated against the flow, and it will indicate the flow measurement. Okay, that kind of sensor can be used. next day we will discuss about temperature sensor today after this, and we will continue our discussion on temperature sensors. After we finish our temperature sensors, there are some other things also, signal conditioning devices, some reviews are to be there, mechanical actuators, electrical actuators, pneumatic and hydraulic actuators. Pneumatic and hydraulic actuators we have already studied in 4th sem, and there is one important aspect of mechatronic system, that is control, part of it. So that control engineering will be started after that. So next day we will discuss on temperature sensors. For that discuss, let us conclude today's class. Okay, thank you everybody.